Okay, let's look at 8.6 example 2 together. So I wrote down a couple of things here on my piece of paper, and it might be helpful if you pause the video and copy down what I have here at the top, but let's go through over what I said. So in example 2, we are going to determine the type of function from a table of values, so like x and y values. So things to look for: if it's a linear function, the y values are going to have a common difference. And remember, that means that they add by a constant amount every time. So if it's like plus 2, plus 2, plus 2, then that's going to be a linear function. An exponential function, the y's have a common ratio, and that means that they multiply by the same amount. So it's going to be like times 2, times 2, times 2. Quadratic is a different kind of pattern that we're looking for. This one is definitely new for us, so just be careful when you're thinking about quadratic and just take some time to listen to how I explain it. For quadratic, the y's have a second common difference. Remember, common difference means that we're again adding, but the first common difference is not going to be the same like linear is. The first common differences are going to be different, but the differences of those first differences, those are what's going to be the same. And I'll show you some examples so you can see what I mean. We're going to go through example 2. This is A. I'm getting this right from our textbook. Example 2, we're going to do A, B, C, and then we'll do an extra example for quadratic just so we can see more examples like it. So we're going to take a look at A. Our first step is to just make sure that the x's are increasing by the same amount, and they're always going to be adding no matter what kind of function it is. And here we see our x's are adding by 1, which is good. Now let's look at our y's. In our y's, we're going from 11 to 8 to 5 to 2 to -1. We are subtracting by 3 each time. So because we're subtracting by 3, that's the same thing as adding a -3. And adding a -3, that's going to be linear. That has a common difference. So this is linear because the y's have a common difference. And just to differentiate here, it's a first common difference versus when we see quadratic, it's called a second common difference. So this is a first common difference. So you can just say common difference. Okay, let's look at example B. Again, we want to check the x's. So we can see here our x's are increasing by 1, which is a good thing. Now let's look at our y's. Our y's are going from 1 to 2 to 4 to 8 to 16. Our y's here are definitely multiplying by 2 every time. When we multiply by the same amount, that's called a common ratio, which means it's going to be an exponential function. So this is exponential because the y's have a common ratio. Again, that means that they multiply by the same amount each time. Okay, let's check out letter C. So in letter C, first look at the x's. Again, we are increasing by a constant amount. We're adding 1 every time. And it doesn't always have to be +1 on the x's. It could be +2 or +3. It just has to be the same in our table. Now let's look at our y's. In our y's, let's see, is it just adding from -1 to -2, that's -1. But then -2 to -1, that would be +1. So it's not a first common difference. Is it multiplying? Well, to get from -1 to -2, that's times 2. But -2 times 2, that would be -4. So it's not multiplying. So that means that we're left with this quadratic option. And let's see if the y's have a second common difference. So we're going to find the first set of differences. We're going to see what do we have to add. So to get from -1 to -2, that's -1. To get from -2 to -1, that's +1. To get from -1 to 2, that's +3. And then to get from 2 to 7, that's +5. Now these are clearly not the same. But look at the difference between these differences that I just found. How do you get from -1 to +1? You add 2. How do you get from 1 to 3? You add 2. How do you get from 3 to 5? You add 2. And look at these. These are called the second difference, and these are the same. So this has a second common difference, making this quadratic. So this is quadratic because the y's have a second common difference. Let's look at another example like this, just so that we can make sure we truly understand what quadratic looks like in a table. So first, this is an extra example. It's not in the book. It's just something that I added here. I'm going to just call it letter D. Let's look at our x's. So our x's are doing the same thing. They are increasing by 1 every time, which is good. Now let's look at our y's. We go 11, 5, 3, 5, 11. You can almost even see that these y's have that symmetry, like how a parabola has symmetry on the graph. That kind of gives it away. So let's right away check to see if it has second common differences. So how do we get from 11 to 5? We minus 6. From 5 to 3, minus 2. From 3 to 5, plus 2. From 5 to 11, plus 6. Now these are clearly not the same, but now let's find the difference between the first differences. How do you get from -6 to -2? You add 4. From -2 to +2, you add 4. From 2 to 6, you add 4. So again, we can see that this is a second common difference, which makes this, again, quadratic. So again, this is a quadratic function because the y's have a second common difference.